Hello, everyone. My name is Cheryl Doughty. I'm currently a NASA postdoctoral program fellow working out of the Goddard Space Flight Center in Maryland. But today I wanted to share with you some of the work I did as part of my PhD at UCLA on a project in collaboration with Stein at the Southern California Coastal Water Research Project. And specifically, this project was part of a larger regional effort known as the Southern California Wetlands Recovery Project. Now, the whole goal of this project is aimed at preserving and restoring coastal wetland area, diversity, and connectivity across the large Southern California region. You can definitely go check out the report for more info on this. But in order to meet some of these goals of preserving and restoring coastal wetlands, it's first important to understand what is at stake in this urban region facing impacts of climate change. And so my role was to quantify potential losses of wetland habitats due to sea level rise. And to do this, we developed a model specifically catered to deal with some of the interesting considerations of the Southern California region. So an important thing to note about this region is that it contains a diverse network of wetlands that are often discrete and constrained in size due to urban development and limited upland migration space. And so as part of this project, we categorized over 100 wetlands into these archetypes, which are groups that represent wetlands of similar form and function that we expect to respond similarly to sea level rise. Now, because this region has a high energy coastline, a good portion of our systems are intermittently opening and closing estuaries. And so here we refer to these as intermediate estuaries. But it's also important to note that some of the other wetland archetypes in this region exhibit similar opening and closing mouth dynamics. Now, these IOCEs, systems are a really important consideration for our adaptation planning in Southern California. So to predict sea level rise driven habitat losses, we developed a model that could quantify potential habitat change. Now we wanted to be able to model every single wetland in the region, regardless of size or typology, so that our regional perspective was as robust as possible, while also reducing spatial gaps in our understanding of sea level rise impacts. So our model was based off of wetland elevation, specifically hypsometry, and predicted changes in elevation and water levels based on model inputs of accretion, sea level rise, and mouth dynamics. Now, a lot of work went into developing this model, and you can definitely check out our paper for more information. But today, I wanted to focus specifically on this mouth dynamics component that we included so that we could better predict changes in these IOCEs. And some of the reasons that we wanted to consider mouth dynamics in our regional model is because there is uncertainty in predicting how estuary mouths may behave in the future. But we know that any changes to the extents and durations of inundation within these estuaries could have a significant impact on wetland habitat distributions. So for this mouth dynamics component of our model, we wanted to gauge the probability of changing mouth states in these IOCEs and similar archetypes, and what those changes would mean to water levels within each estuary. So we hypothesized that any increase in sea level will increase the frequency of estuary closure and induce a shift in dominant mouth state, and will ultimately increase water levels within a site. So to test this hypothesis, we conducted a simplified modeling approach based on a closure index, and models from the work of Dean Behrens and John Largier on inlet morphology and lagoon hydrology, designed specifically for estuaries in California and the West Coast of the United States. So we used about 20 years worth of data. We used NOAA tide level data, sea dip wave data, and modeled watershed runoff data from the Southern California Coastal Water Research Project. Now, to predict future closure indices, we created a synthetic daily time series based on these data inputs by manipulating wave and tidal inputs to reflect sea level rise projections of 0.6 meters for 2050 and 1.7 meters of sea level rise for 2100. Now, the first step in this simplified mouth dynamics model is estimating the daily closure risk. So wave power was estimated from significant wave height and wave period, and tidal power was calculated from daily data on tidal range and tidal prism based on water surface area derived from our hypsometric curves specific to each estuary. Now, tidal power also takes into account the size of the estuary mouth and the daily runoff data. And this closure index is a simple ratio of wave power to tidal power that tells us when the probability of closure is high or low. Then we used this estimated closure index to estimate water levels in the lagoon using a simplified model based on the work of Dane Behrens, and you can check out his 2015 paper for more info on this. But we assumed when the estuary risk was low, that the water levels in the estuary would simply track with sea level rise. However, when the risk was estimated to be high, we assumed that the estuary would close and that the changes in the system water level would be determined by the starting conditions in the estuary and net river runoff after considering evaporation. And so again, this is a pretty simplified approach, but it allows us to use the data that we have available for a number of IOCEs in this region in order to gauge how estuary closures and water levels could change in the future with sea level rise. So this mouth dynamics analysis, it showed us that a 60 centimeter increase in sea level rise would increase estuary closure on average about 8% across the archetypes where we had enough data to do this modeling. A 1.7 meter increase in sea level would increase the percent of time on average by 28%. So you can see that small creeks and lagoons that are already pretty prone to closure in this region are expected to have even more closures in the future with sea level rise based on this simplified model. And the risk of closure in these intermediate estuaries, our IOCEs, are comparatively not as drastic, but we are expecting more closures with sea level rise. And so these large river valleys, interestingly, showed no real changes in the amount of high risk closure, probably due to runoff data. But that's also an important part of this model that has yet to be worked out in the future with climate change. And so you can also see that fragmented river valleys here and open bays and harbors, these archetypes didn't have the data to be modeled, either because these systems don't typically have any associated river inputs, or their mouths have been hardened or modified by humans. So we also considered estuaries that have been modified or jettied or continually go through management like dredging to keep mouths open. Those were also considered for each of these estuaries. So you can see though that overall, from the simplified approach, we're expecting an increased likelihood of closure for some of these systems under future sea level rise conditions. Now, when these systems underwent high closure, the changes in estuary water levels are expected to increase as well. So there's about 40 centimeters increase with 0.6 meters of sea level rise and about 143 centimeters with 1.7 meters of sea level rise across the board. And again, we couldn't model where we didn't have any data or where closure risk was estimated at 0. So there's always much more work to be done in terms of data needs and improving these models. to really create robust predictions of how these estuaries are likely to change in the future. So beyond just sea level rise, also thinking about changes in runoff, water management, and changes in precipitation regimes and things like that. So again, a lot more improvements to be made. But again, this simplified approach really allowed us to take a first pass at what we can expect in the future. And so from this modeling effort, we were able to kind of account for some of these considerations specific to IOCEs in our region and use this information to improve our sea level rise driven habitat response model. And in order to predict how these different subtidal, mudflat, and vegetated marsh habitats would change in the future. So some of these inputs from the model basically got binned into estimated closure risk for each of these estuaries, and the inputs of inundation included this mouth dynamics components for how much water levels would increase in a specific estuary over time. So overall, when we fed this information back into our sea level rise habitat response model, we were able to predict how habitat distributions would change in the future. So here in this figure, you can see all of the 7 or so different archetypes that we had and the proportion of wetland areas falling into subtidal, unvegetated flat, and vegetated marsh habitats for each of these 3 different sea level rise scenarios. And so you can see that large vegetation archetypes are expected to lose the most habitat, and intermediate estuaries among these show the greatest potential increases in mudflat habitats. Now, incorporating this modeling effort on IOCEs provides us with a better understanding of how vulnerable these systems are and how vulnerable all the systems are throughout this large geographic region. And it really provides us with a holistic perspective of risk that allows us to better plan for and adapt to a future of climate change. So again, much more work to be done, but this was our first step in providing vulnerability in terms of wetland habitat loss in the Southern California region. Again, designed specifically for this region to account for some of these considerations like intermittently opening and closing estuaries. And so with that, thank you very much for your attention. And thanks again to the organizers for this exciting inaugural meeting. I'm happy to be a part of it and happy to take any questions. Thank you very much.